So in the last video, we dealt with the idea that the binomial theorem follows a continuous pattern where you find that in order for you to get from the first term to the last term, you need to drop a and then raise b. And then we dealt with the whole idea of expanding on what the idea of dropping a and raising b really means, or the whole process behind getting from the first term to the last term. So now we're going to expand more on some of the patterns on the binomial theorem. So we first stated that it follows a continuous pattern where you find that when n is odd within the middle term, you'll find that a and b are both powered by identical halves of n. So now we want to continue on some of those patterns. So as well, I had stated some of the patterns within the last video that, well, the binomial theorem follows this pattern of a plus b's to the power n. So where n is either odd or even, you'll find that there's always a switching of exponents in the terms between a is to the power n and b is to the power n. So when n is even, the switching of exponents becomes visible after the middle term and then when n is odd, the switching of exponents becomes visible after the middle two terms. And so in both cases, the switching of exponents follows a continuous pattern of switching exponents. So in a plus b is to the power n, where n is odd, you'll find that the number of terms produced will always be even, such as, let us consider, for example, well, a plus b is to the power 1. Two terms are being produced, and we know that 2 is an even number. Let's consider then, well, we know that the power of a plus b, so which is 1 in this case, that's an odd number, and the number of terms is an even number, which is 2. So what about a plus b to the power 3? Well, we'll find that how many terms are being produced? 4. And then what about a plus b is to the power 5? The number of terms produced will always be 6. So the switching of exponents, can be shown by this pattern. I like to use a is to the power n plus a continuous pattern of the terms in between, and then I denote the switching of terms using the letters e and f, like a is to the power e, b is to the power f. And so when we then come on to the next term, you'll find that we have a is to the power g, b is to the power h, and then plus. What you notice is that these middle two terms, the exponents have now been switched, because now here a is powered by h, b is powered by g. Unlike here where a is powered by g, b is powered by h. It's the same thing with this next term, which is a is to the power f, b is to the power e. So it's similar to this case. But now it follows a switching pattern of exponents with this term right here. So instead here, a is powered by f and b is powered by e. So it goes on and on and on following this pattern until it gets to the last term, which is our b is to the power n. And so now let us show the pattern of switching of exponents, as I had stated, can be shown in this way. So this here represents a case where n is like some even number. So when there's an even number, you'll find that it starts with a to the power n, follows on and on with a continuous pattern of terms, and then plus, well, a is to the power e, b is to the power f, and then a is to the power g, b is to the power h, plus. So this is then the middle term where you find that a and b are powered by an identical half of n, and then a is to the power h and b is to the power g. So you can notice that between these two terms there's like a continuous pattern of switching terms. So here a is powered by g, here b is powered by h, and here a is powered by h, b is powered by g. Similar case in between these terms. So a is powered by f here and b is powered by e, unlike here where a is powered by e and b is powered by f. So where n is even, for an example, let's take a plus b is to the, well, let's take for an example a plus b is to the power 7. What you'll notice is that, well, we're going to have a is to the power 7, and then we'll have a to the 6th, b, a to the 5th, b to the 2nd, a to the 4th, b to the 3rd, and then a to the 3rd, b to the power 4, and then a to the 2nd, b to the 5th, and then a, b to the 6th, and then b is to the power 7. So what you've noticed is that here, well, these are the middle two terms. So this is a case where n is like an odd number. So these are the middle two terms, and here we start seeing this pattern of switching exponents. So the exponents in this term switched with the exponents in this term, and then here in between these two terms we start seeing another pattern of switching exponents. And so here in this term we start seeing another pattern of switching exponents. And then here in between these two terms as well, we also start seeing a pattern of switching exponents, because here a is powered by 1, b is powered by 6, but here a is powered by 6, b is powered by 1. Here a is powered by 5, b is powered by 2, unlike here where a is powered by 2, b is powered by 5. And then also here a is powered by 4, b is powered by 3. But here you'll find that a is powered by 3, b is then powered by 4. So let us then consider a case where n is like an even number. You'll find that, let's say a plus b is to the power 8, a to the power 8 plus a is to the power 7, b, a to the 6th, b to the 2nd, plus a to the 5th, b to the 3rd, and then a to the 4th, b to the 4th. So this is the middle term. Again, this is powered by an identical half of n, which is our n is 8. So a and b, that's why then they are powered by 4, which is like this half of 8. And then here you have a to the power 3rd, b to the 5th, a to the 2nd, b to the 6th, a to the 1st, if I would put it this way, b to the 7th, and then a to the power 8. So here as well, we notice the same pattern. A is powered by 7, b is powered by 1. Here we notice that a is powered by 1, b is powered to 7. Here a is powered by 6, b is powered by 2. But here a is powered by 2, b is powered by 6. Here we notice that a is powered by 5, and then b is powered by 3. But here we notice that a is powered by 3, b is powered by 5. And then the middle term, where a and b have identical halves of n. And so yeah, that was basically everything I had to say about the binomial theorem. So in order to understand the gist of everything that I have been talking about with regards to the binomial theorem, you might need to watch all the videos within my playlist about the binomial theorem, and some of the other videos I've put in my description, in the description of like this video and my other videos, with regards to even other videos that I would recommend that you watch with regards to the binomial theorem.